Good morning or afternoon or whatever is going on in your part of the world. We're here to talk today about, right, you guessed it, electricity. Now you say you've already talked about electricity. No. You've talked about static electricity. What we're going to talk about today is why you need the adjective static. You need it because electricity is only static in special occasions. More frequently, the electricity can move, and it moves in a way that we call it electric current. So if we take the model we had from static electricity, which is to say that we have charged particles, these charges, of course, we've already, and it's important to remember, we've already said, like charges repel. Now that really makes you wonder about static electricity, I hope. Did you think about this? You didn't, did you? Why would charges that repel each other sit still in one place? Why would they be static? They're static because the atomic structure of the material that we're talking about clings to its electrons so strongly that even when they're repelled by their neighbors, they're not free to move. If we take a metal, it turns out that those electrons are not really strongly bound. And so if we put some charge in one end of a wire, it tries to move out of its own way. It's getting away from its neighbors, and it turns out it's pushing electrons ahead of itself, and pretty soon we've got electrons moving through the wire. We have electric current. What would that be like? Would it be like cars on a highway? And here we can see that these cars are moving down. The highway would be the wire. The cars are the charges. There are some good parts to this metaphor. Remember, the price of metaphor is constant vigilance. Is this a good model? Well, it's a good model in that each of those cars is not at all interested in getting close to any other car. Now, it's not because there are electrical forces repelling them. There are financial forces. If you get too close to another car, it's going to cost you. But you act the same. You slow down before you run into one ahead of you. You speed up if somebody's riding on your tail. Okay, that's something that's similar to electricity. Something that's not similar is that if we're looking at cars, mostly we're interested in where does the car go. We're interested in the car. In the case of electricity, we're really not interested in the electron. We're interested in the energy the electron can deliver. It's going to move through the wire. And in a mechanical example, if we were talking about cars, it's going to get to the end of the road and run into something, and we want to know how big an effect it can have. Certainly that's not the way we use cars. Something that acts a little more like that might be water. Lots and lots of particles. The water flows down the stream bed. And let's imagine there's a mill just out of sight down that stream. The mill runs with a water wheel. This water comes down, and of course the guy running the mill is very interested in getting enough energy to make the wheel turn, which in turn will let maybe his grinding wheel work or whatever he's using his mill power for. So what measurements might he do on the stream to find out whether there's enough energy for him to run the mill that day? Well, certainly he'd care how much water was moving. We might call that the current. And conceivably we could measure it in gallons per minute. But he would also be interested in how much energy each gallon had. Now, measuring energy is a little complicated, but we know that energy is just 1/2 mv squared. So we know that a gallon of water is a little bit less than 4 kilograms. And so we got a mass. If we measure the velocity, 1/2 mv squared, we can get the energy per gallon going down there. And so now we've got gallons per minute, we've got energy per gallon. He can sit down and say, can we run today? So electrically, we've got a similar situation. What kind of measurements are we going to take? We're going to take a flow rate, which we're not measuring water now, so it won't be gallons. It's going to be charge. Electrons per minute? No. A, electrons are too small, and B, minutes are too big. So let's take a big lump of electrons, a lump we've talked about in the past, a coulomb. 6 billion electrons. Billion is 10 to the 9, billions is 10 to the 18th. 6 times 10 to the 18th electrons. A lot of them, but remember they are tiny. And we're going to say how many of those coulombs go by every second. That unit, coulombs per second, is called an amp. There are meters that measure it. They're called current meters or ammeters. What about energy? Well, energy, whether it's fluids or electricity, is measured in joules. Once again, we've got joules, but it's not joules per gallon anymore. The thing that's moving isn't a gallon of charge, it's a coulomb of charge. And so we're interested in how much energy each coulomb of charge has, a joule per coulomb. So what's that unit going to be? We're going to name it after another scientist. It's the volt. So a volt is a measure of energy per charge. It is a potential energy, meaning that if a battery is a 9-volt battery, the energy is not realized yet. It says that if we let a coulomb of charge flow every second, which would be what current? Right? You're all saying 1 amp. If an amp flows, we will get 9 joules of energy, okay, in that second. And so now we've got our electric units. It is critical to know what those units are. Mostly people kind of blur them together and call them electricity. But we really need to know what does each of them measure, because that's going to let us know what we've learned about the behavior by the way they change. If we take a look at how this might go mechanically, if we take our wire and put an electron in it, you note that it just sits there and does nothing. And it does that because there's no potential difference. There's no energy change in going anywhere, so there's no reason to do it. Electrically, I could raise the electric potential energy by making this end negative. It would have a high potential energy, and this electron would move away from it at increasing speed, picking up that potential and turning it into realized energy of motion. Mechanically, I can do that here because this is not a charged ball bearing, it's a ball bearing with mass. And so the field that affects it is gravity, and if we give this gravitational potential energy, it begins to move and runs through the wire. At the end of that wire, it would have run out of energy. That's what a battery's for. It is roughly the equivalent of a ski lift. And so we take our electron, we bring it back here, the ski lift brings it back up the mountain, and in it goes, and it delivers that energy by going back down the potential hill. And so this is what we mean by a potential difference. It makes lots of sense mechanically if you think of gravity. The electrical behavior is exactly the same. It's just that electrons respond to electric forces, not gravitational ones. Here we've got all the makings of an electric circuit. And circuit is really an important term, because remember we said charge is balanced in all pieces of matter, and unless we've rubbed them and charged them electrically. But we have an equal number of electrons and protons, and the net charge is 0. So that means that if I want a charge to move in something, I've got to let the repulsion effect take care of itself. So I can't just take a single wire and shove an electron in it. Now we've got an unbalanced charge and the electron doesn't want to stay. And so what we're going to do is take a battery. Okay, this is a standard 6-volt battery. The negative terminal is here, positive terminal here. In general, to keep track of that quickly, we use red wires connected to the positive and black wires to the negative. In this case, we are going to run electrons out of the negative terminal through this wire to this light bulb, back through this wire, and we have a closed circuit. And so every time an electron enters at this end, we've got that pulse of each chain reaction collision, electrons bumping each other. An electron leaves here and goes into the battery. The electrons that leave here have got 6 volts of electric potential energy. That means every coulomb that leaves here is capable of delivering 6 joules of energy to whatever device we're connected to. When it gives up that energy, it no longer has any, and it's simply moved along by the fact that other negative charges are arriving behind it and repelling it. It comes back here, and in the case of a battery, we are energizing those electrons through a chemical reaction. The size of the battery indicates how much chemistry is there, which of course is an indicator of how long it will last. Small batteries can do what they do for a short time. The voltage has to do with the strength of the chemical reaction. And of course what we discovered long ago, and Mr. Volta was part of that, was that if we take one chemical reaction and put it after another, we get to add their potential energies. And so typically a chemical reaction generates about a 1.5 volt potential energy. If we want more, we have to stack those chemical reactions in series. And so to get a 6-volt battery, there are 4 of them going on in here, packaged as a single unit. Let's see if this all works. We hook this up, and if we note carefully, the bulb is lit. It's not terribly bright because it would like a bit more energy to really get moving. But at this point in time, it's lit a little bit. Let's see if some contrast helps, and if we disconnect it and reconnect it, we can see it move. If we leave it connected, we're going to drain the battery, and the battery has a finite life. So now that you've seen the battery and seen the way it goes, we have a closed loop running here. We're going to suggest that in the future we're going to use a plug-in electric power supply. This is indistinguishable from a battery, and so we've got a power supply. We send negatives out, they go through the light bulb, come back around and go in here. If we turn this guy on, we can raise the power, and now we can see we can deliver more than 6 volts with this power supply, and you can see that the bulb lights. If I want to measure current, I actually need to get everything that moves through the wires to move through the sensing device. And in order to get that to happen, I'm going to take a multimeter. And a multimeter is a device that can measure volts. The wiggly line over the V means alternating current. The bar and dots means direct. So I can measure alternating and direct volts. I can measure amps and milliamps, which is to say thousandths of an amp. Because remember, an amp is a coulomb per second. When they first invented the name, their sensing devices were pretty crude, and you needed a lot of current to see it. Today we've got very efficient devices and very good measurement tools, and frequently we only need 1,000th of an amp. And so milliamps are probably used more often. If I turn this around to read amps, possibly you can see that that amp reading, let's get the glare off it, reads AC, and then the bar and dots for DC, if we move that up, are the yellow, which means I can shift it. Here it reads amps AC. Let's ask it to read DC. And now what we have to do is set up a situation where the negative side of the circuit connects to the black lead, which says common, and we're going to have a look at amps. So the wire that's closest to the positive source of electricity is going to go here. The one closest to the negative side goes here. Remember, we said we need to insert this into the circuit. If you note this wire, if I track this wire back to the power supply, it's the negative terminal. And so I'm going to plug it here. And if I track this wire back, it's going to the positive terminal. So it's going to go here. 0.138 amps. And we can make the bulb a little brighter, and we see that we have more current. And if we take it all the way up, we get close to 0.2 amps. As we come back down, as the current gets lower, that means fewer charges carrying less energy. It's quite apparent that the bulb is producing less light energy. So now we're interested in making the other measurement. So let's briefly move this out of the way and make sure that you know where we are so far. We have our circuit, negative lead to light bulb to current meter back to power supply. One closed loop. Please notice that the current meter basically becomes a part of the wire. It needs to be easy for the electricity to go through, and it's critically important that all the moving charges go through this meter so they get counted. But now we're interested in voltage. How much does the electric potential energy change as it moves through this light bulb? And so we set up our meter here. It is also a multimeter, and we're going to set it to DC volts. The connections are our negative common, and the positive lead goes to the positive terminal labeled V for volts. But now let's talk about how we connect it. We are interested in saying, all right, what is our baseline, our starting point? Because like all other potential energies, it is a difference, a change. And so let's put the starting point over here where the negative charge arrives and has yet to use any of its energy in the light bulb. We are then going to check what kind of energy does the charge have after it has finished working on the light bulb. Now notice this is a very different connection. The electricity comes here and has the choice of going through the light bulb or going through the meter. The meter has been placed in an area where previously there were no connections. The meter has in essence taken the place of air. If we don't want to change the circuit, the meter better look like air to the electricity, which is to say, it should be very hard to go through. So that means almost all the electricity goes through the light bulb, and only a very small fraction of it goes through the voltmeter. So the voltmeter is doing statistical sampling. It's checking on the energy level of just a few charges and saying, what did we have when we started and what do we have when we're done? And it is going to report that difference. And that will tell us how much energy got used in making the light bulb light. So let's take a look at how that works. We're going to turn up this energy, and we're going to see that both the voltmeter and the ammeter are changing their values. The bulb lights. Let's go back to where it's barely lit. And so the bulb doesn't light until we're approaching 2 volts. and we notice that the current is about 0.08 of an amp, and as we raise the voltage, we see that the current rises. Now, light bulbs are kind of complicated devices, and so when we look into the way these two numbers affect one another, we're going to switch to a simpler device. Because what we have here is the kind of thing that makes a scientist salivate. We've got two different measurements that seem to be related. The average scientist would say, all right, let's measure these, let's get a data table, let's graph it, and let's see if there's a pattern to that behavior. So we're going to do just that, but we are going to replace this light bulb with a device we call a resistor. Now, this is a really big rendition, and what goes on with a resistor is we get wire that's harder to move through electrically, and we get a lot of it. So this is coils of it, and we hook up to either end, and now when the electricity goes in, unlike the copper wires we have here, this takes effort. The effort expended by the electricity turns to heat, as it did in the light bulb. The difference is that this never gets so hot it glows, because when things get that hot, their electrical properties change. And so we would like to examine first a situation that's not so complicated. It doesn't get that hot. This is a very large resistor that could handle lots of power. With this, we can kind of see what the process is going to be. What we're going to use is a smaller version of this. And so if you look at electronic circuits, you find that in most instances, the devices that act this way are brown plastic cylinders, not terribly large. They frequently have color bands on them, which, if you know the code, will let you determine what kind of a value they have. The electricity here will enter that connection, go through here, come out here, and electrical energy will be used because this warms up. Well, maybe we ought to stop here. I'm beginning to realize, yeah, I'm enthusiastic. I know you're really ready to roll. You're salivating over the data we could collect. But if we do that now, we'll have done Ohm's Law Lab. And we'll have done it without your opportunity to have some feedback with the person running the equipment. So let's stop. We'll see you at Ohm's Law Lab. In that instance, you're going to be working with the same equipment. You need to hook it up the same way, but you're going to be able to say, what if we do this? So think about that. Think about what you'd like to manipulate there, and we'll see you in Ohm's Law Lab. Thanks for your attention.